Computers are marvelous feats of engineering. They've revolutionized every aspect of modern life, from mathematics, medicine, and physics, to actually important shit like playing Fortnite. Due to how quickly computers have advanced, we often forget that there was once a world without them. But as modern computers edge their physical limits by packing billions of transistors into tiny chips, I'd like us to take a more modest approach and build a basic computer that embraces its limitations and allows us to appreciate the simple yet elegant inner workings of the device that has changed humanity forever. In this video, the goal is to build a computer that's at least more powerful than something from the 1970s. Our opponent, the Intel 4004, designed by Can I say this guy's name? The point is, it had a whole team behind it, and people would fork over $600 for this bad boy back in the day. Let's see if we can beat Mr. Fagin and his homeboy at their game. But hey, listen.
One scientist. I'm just one scientist.
A computer is just an electric circuit, and this is the most basic circuit you can build. You need power, some sort of output device that does something useful, and some piece of wire that connects everything together in a complete loop from positive to negative. You also need a resistor, which protects our components from getting fried by the power. We're gonna need a bunch of these, thousands in fact. Luckily, each resistor is worth about as much as the Zimbabwean dollar, so they won't cost much. Well, now what? Just having this light on is almost as boring as a Naruto episode. Almost. Let's do something a bit more interesting. Let's break the connection in our conductor and add a switch here. We can now control the light bulb. Why stop at one switch? If you arrange two switches like this, you create two disconnects in the wire. Both switches have to be pressed to complete the circuit. Switch A and switch B have to be pressed at the same time for the bulb to light up. If you arrange two switches like this, then pressing switch A or switch B, or both, will turn the light on. We can also turn the light off by short-circuiting the pins of our bulb. This creates a path with no resistance that the electricity can take. I'm skipping over the details here because there are many ways you could wire these circuits up. You could use breadboards like I'm doing here, but the connections are infamous for being really flimsy. The best option would be to use high-quality PCBs from PCBWay, our sponsor. Thanks to PCBWay, turning your circuit ideas into reality is as easy as clicking your mouse a few times. This is because they've made it so simple to use their built-in plugins on KiCad. These boards are so high quality that they make even my soldering look half decent. As if that wasn't enough, you get full creative freedom of how you want your board to look, and trust me, this board looks incredible. They also have 3D printing, CNC machining, and laser cutting services that we'll make use of in future videos. Thanks again to PCBWay for sponsoring this video and making these high quality boards. This circuit's actually really useful, and we'll talk about this a little later in the video. What's interesting is, these circuits are basically making decisions. They consider the inputs and decide what the output should be. Since making decisions needs some sort of logic, we can call these circuits logic gates. And it's useful to keep a table of all the possible inputs and outputs each logic circuit can have. Yeah, we deal with these on and off states a lot, so we don't want to have to write out all these words, especially not when we start building bigger circuits. So we'll use a 0 to represent an off, and a 1 to represent an on. Imagine if we could connect multiple decision-making circuits together. We'd basically be tricking electricity into thinking. We unfortunately can't do that because these circuits take in physical forces as inputs and produce electrical signals as outputs. We could turn the electrical signals into physical forces, but then we'd have to use these mechanical switches called relays. We don't like relays here. The other option is to use transistors, and that allows us to chain a bunch of them in a larger circuit. I'm skipping over the circuit details here because I don't want to run out of content.
This is all I got.
And it's kind of a snooze fest. It's more boring than listening to a J. Cole album. Now that we can connect multiple logic gates together, we can build circuits that can do literally anything. This is like when Jin Woo-sung got access to the system in solo leveling. We're now ridiculously overpowered. If we know the inputs of a circuit and the outputs it should produce, then we can build that circuit using a combination of these logic gates. So let's actually start building the computer. Hey, a computer ought to be able to compute, right? Let's start with some maths. But how would the computer even know what a number is? Normally, we have 10 base numbers to work with, 0 to 9. We start at 0, add 1 and go down the list. We're counting. But what if we reach the end of the list? There are obviously numbers larger than 9, so we still want to count up from 9. Something weird happens when you add 1 to 9 though. The answer is 10. I know this is exciting, but try to keep your underwear on. What's weird is 10 is not its own number. It's made of two numbers that we already have in our list, 0 and 1. Look at the first digit, 0. Notice how we've just gone back to the start of the list and added a 1 to the next column. Then counting continues as it would normally. So this column tells us when we've counted past 10 numbers. We call it our tens place. We can keep going to allow us to handle even larger numbers. The rule being, whenever we run out of digits, we just add 1 to the next column and wrap back around. We can take a similar approach to use ones and zeros to represent larger numbers. So just like we did before, you start at 0, add 1, and we've already run out of numbers. But for us to keep counting, we have to wrap around, then add 1 to the next column. So this is 2 in binary. Chucks, this is really difficult to grasp. Is it possible to build a circuit that converts binary numbers to normal numbers, just to make it easier to follow? Like we said before, if you know the inputs of a circuit, and we know what the outputs should be, then we can build that circuit. So build it. If you thought I'd waste 2 days designing a binary to decimal converter just for a 2-second gag, you thought right, because that's exactly what I did. This circuit actually has a lot going on here, so we'll build it from the ground up in a future video. We have numbers and we have logic gates. Let's build a machine that can add 2 numbers together. Since we only have zeros and ones to work with, we can only ever add inputs 0 plus 0, 0 plus 1, 1 plus 0, or 1 plus 1. I don't like that the last answer has 2 digits but the first 3 have 1. I'll add zeros here just for continuity. Splitting these 2 digits allows us to tackle them individually. This looks really familiar, doesn't it? It's the AND gate we built before, but this logic gate is new, so we're on our own. We need to design a circuit that satisfies this truth table. To do this, we just attack the cases when it should output a 1. It outputs a 1 if A is a 1, and B is not a 1, or if A is not a 1, and B is a 1. Reading the table out gives you everything you need to design the circuit. We'll use a different and way better circuit later, but this will do for now. This circuit is called an XOR gate.
You should just use K-maps. It's way easier to develop the circuit that way.
The fuck is a K-map? Okay, let's see. Whoa, the organic chemistry tutor. Hold on. Is this homework? I failed my actual exams. I'm not studying how to make this stuff. It gets boring and it's gonna feel like a chore. We're just gonna wing it here. Combining these 2 circuits gives us a basic adder. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 1, 0. Okay, let's add bigger numbers. Let's add 9 plus 13, 1 column at a time. 1 plus 1, that's 0 carry 1, and now we have to add 3 numbers. Our adder only has 2 inputs, so we still need to add a bit of circuitry to it to account for the carry from the previous column. This is easily solved by just adding the carry to the solution. So we take the sum and add 1 to it. We can easily just chain 2 half adders together, and we add this OR gate here for the carry signal. This OR gate makes up for the fact that one of the inputs is invisible to this half adder. This circuit is the completed full adder. The more full adders you have working in parallel, the more information you can process at a time. This is where the concept of bits come in. When someone says they've built an 8-bit computer, it means it can process 8 bits or 8 binary digits at a time. I'm not mentally ill, so I won't be hand wiring an 8-bit computer from individual transistors, let alone 16 bits. We're building a 4-bit computer. Limited as it may seem, we could still do some very cool stuff with it, like this project by 3D Sage. I know I keep gobbling this project's nuts, but I really do find it impressive. We're done with addition. What about subtraction, multiplication, division, trigonometry, hyperbolic functions, calculus? I hope you're catching what I'm hinting at here. There's just so much we could add to this computer, but if we did all that, then we'd never finish. So we need to come up with a list of the most essential functions we want our computers to be able to perform. These can be used later to achieve more complex functions in code. These functions are all combined into a single circuit called the arithmetic and logic unit. This is the heart of the CPU. The more capable the ALU is, the more powerful the CPU is. The Intel 4004 could add and subtract. We at least want to match that. Here's how we're gonna beat the faggot squad. Our ALU should also be able to perform logical operations, like AND, OR, and NOT. I think it would be an extra point for us if we could achieve all these functions without adding too many transistors. Let's revisit the circuit we used for the adder because we can save a bunch of transistors here. When we designed the XOR gate before, we attacked the outputs of the ones it produced. Now let's attack the zeros. We get a 0 if A is not a 1 and B is not a 1, or if A is a 1 and B is a 1. And because we want our outputs to be 1s, we just invert the output. And it turns out this circuit is equivalent to the XOR gate we needed. What makes this circuit better is because we're using more inverted gates. We love inverted gates here because they use fewer transistors. Notice how if we use the circuit to build our half adder, this AND gate and this AND gate do the exact same thing. So we don't need an extra AND gate. That saved us 4 whole transistors. It doesn't seem like much, but it really does scale. Because a 4-bit adder now only takes 68 transistors when it would have taken 100 before. We can reinvest those extra transistors back into the ALU to add more functionality. Now we can get a lot more functionality out of the circuit. Not only do we get A plus B from the output, we can also take this output, which coincidentally is A and B, and this output is also A nor B. We've already checked off most of the functions we wanted our ALU to have. We could also get A XOR B, but the XOR output is affected by the carry from the previous stage, and that'll only cost us 3 AND gates. We can now add, AND, NOR, and XOR at the cost of only about 70 transistors. We said we wanted subtraction too, so let's handle that. Subtraction is just adding negative numbers. So we can just tell the computer to add a negative number. But computers don't have a concept of positive and negative numbers. So we kind of have to fake it using a clever trick. I tried to script this explanation so many times, but it was more boring than watching a classical chess match. I'm sure you're not gonna sit through it. I'll make another more technical video, but for now, just know that to get a negative binary number, you have to invert all the bits in the number and then add 1 to it. So to get A minus B, we need to add A to B inverted, then add 1 to the final answer. So it'd benefit us if we could build a circuit that could invert a number whenever we wanted it to. Let's drop a truth table of what we want. When the negation signal is off, we wanted to just copy the input to the output. If the negation signal is on, then we wanted to give the opposite of the input. And what do you know? This is just the XOR gate. So adding this negation circuit to our B input allows us to add and subtract using the same circuit. That handles negation, but what about adding 1? You're right. That's why our first adder has a carry in signal. We could just add 1 through the carry. Now we can add, subtract, AND, NOR, and XOR. One less clever addition would be the ability to send it in as 0 to either input. This will allow us to see the value stored in the registers without having to add a bunch of logic circuitry. This circuit is special because it does so much with so little circuitry. It ticks off all the functions we wanted, and it even adds the extra XOR function, which would have been a pain in the dick to do in software. And we've done it! We've designed an ALU more capable than the Intel 4004. Now we just have to design stuff around it that can take advantage of all this power. And because we're designing this from scratch, we know all the intimate details of its inner workings, so we know all the little loopholes and exploits we can take advantage of to squeeze all the juice out of it. It's crazy how this complex system with so many moving parts is built from something as basic as switches. Every single transistor, however insignificant it may seem, doesn't realize its own importance. It doesn't know what it's doing or what it's doing it for. However, it contributes to the overall result. In combination, these switches build a machine that can add numbers faster than a Romanian can snatch a wallet. There's something very calming and humbling about building order from disorder. The scaling complexity makes me draw parallels to other things, like life and the universe itself. Anyways, I'm a one-man workhorse. My videos take a long time to script and edit, so if you can't wait and just want to learn how computers work, you can check out the book But How Do It Know by J. Clark Scott. The design is very well explained on the Learning 021 channel. And of course, Benita is the GOAT, closely followed by Sebastian Legou's entertaining videos, and the Global Science Network. This guy is cooking up neurons on breadboards. Remember kids, Cody is not suicidal. Another thing you could do is search up transistor CPU in Japanese, and you'll find a bunch of blogs that detail some cool designs.